I'm going to take you through a method that you can use to help you estimate the roots of functions. Now, this is something that we've done a lot of in the past. When we are working with quadratic functions, we use things like the quadratic formula to help us find the x-intercepts or the roots of the parabolas we were working with. When we work with polynomial functions and rational functions, we use things like factor theorem to help us factor those functions so that we could set them equal to 0 and then solve for the x-intercepts or the roots. And when those things didn't work, we could always take our functions and plug them into things like Desmos or our graphing calculators and use technology to help us find the roots of functions. But sometimes those methods aren't available to us or they don't work. So this is another strategy that we can use to help us find the values of roots of functions, and it's called Newton's method. And basically, Newton's method uses the concept of a linear approximation to help us estimate the roots of functions or the x-intercepts of functions. So here I have a picture of a function. I'll zoom in on it here. So the function here is in navy blue. And what I want to do is I want to be able to figure out what this x value is right here. So what is the root of this function? When does it hit the x-axis? What is the x-intercept? What is the 0? All those different ways of asking the same thing. So the idea here is that we're going to take a value that hopefully is close to it, a first estimate right here. So I'm just going to call this value x naught. And this value x naught is connected to a y value. So I can plug this x naught into my function and I can get a point on my function x naught f at x naught. And through this point, I can draw a tangent line. And I can use a linear approximation to help me determine the equation of this tangent line. Now you'll recall in the past we've used linear approximations or these tangent lines to help us estimate the values of other y values that are close to this point. But in this case, we're going to use this tangent line to help us estimate the root. So you'll notice if I follow this tangent line down until it hits the x-axis, I generate a new point, x, I'll call this x1, that has a y-coordinate of 0. So when I have this tangent line and I set the y value equal to 0, I get this new point, x1. And you'll notice that x1 is closer to my true root than x naught. So what we're going to do is we're going to start off with our linear approximation formula, which is L at x equals f at a plus f prime at a times x minus a. And I'm going to substitute in my first estimate, which I'm going to call f naught. I'm going to sub that in for a. I'm going to sub in y equals 0 because I want to figure out the x value, x1, that occurs when y is equal to 0. And I know that this x value, my x1, is going to be a better estimate of my true root than my original estimate x naught, okay? So if I take my formula and I sub in my values, I get my L at x, which is my y value, so I'm going to put in 0 for that. And then I get f at x naught plus f prime at x naught times x1 minus x naught. So my x1 is my new x value that goes with y equals 0. So what I want to do is I want to come up with a formula that will allow us to calculate the value of x1. So I'm going to take this formula that I've created and I'm going to rearrange it. So expand out my bracket here and rearrange it to isolate for x1. And in this case, I get x1 is equal to negative f at x naught over f prime at x naught plus x naught. Okay? So that's going to give us an estimate or a value x1 right here. Well, you can see x1 is still pretty far away from my true root. So let's see if we can get even better. So I'm going to take I'm going to use the same strategy that I used here to get my x1 to get a closer point, x2, to my true root. So I'm going to take my x1, I'm going to plug it into my function to get a point on my function, x1, f at x1. I'm going to use my linear approximation to come up with a tangent through that point. And I'm going to set that tangent or linear approximation equal to 0 once again to figure out the x value that occurs when y is equal to 0. And you can see then that this x value here is going to be even better estimate than this x value was here. And again, there's still a little bit of room here, so I'm going to repeat the process again. So I'm going to take my x2, I'm going to sub it into my function, create a new tangent line. It'll get closer and closer and closer to my true root the more times that I do this, okay? So if I look down here, I'm going to repeat this process over and over again until I get closer and closer to my true root. So I know that if x1 equals negative f at x naught over f prime x naught plus x naught, then x2 is going to be equal to negative f at x1, because that was the point before it, over f prime at x1 plus x1. And x3 is going to be equal to negative f at x2 over f prime at x2 plus x2, and so on. So in general then, I can say that any xn is equal to negative f at xn minus 1, so the x value before xn, over f prime at x at n minus 1 plus xn minus 1. And this here is the formula that I can use over and over and over again to make a linear use linear approximation that will allow me to get closer and closer and closer to the value of x. That is the value of x that occurs when y equals 0. And this will then be the root, because we know that roots or x-intercepts occur when y equals 0. So to show you how this works, I'm going to take you through an example. So in this example, I'm going to look at a function, and this function, I'll just zoom out here, is f at x equals x to the power of 3 minus 3x plus 1. And what I want to do is I want to see if I can find the x-intercept, or the root of this function, on this interval 1, 2. So on the closed interval 1, 2, where is this going to hit the x-axis? And I'm going to use Newton's method to do this. So because Newton's method uses both the function and the derivative, I'm going to calculate the derivative. So I get f prime at x equals 3x squared minus 3. And I'm going to choose a value to start with. Well, I'm going to just choose the value 2 as my initial estimate because it's just the endpoint of my interval here. So I'm going to start with x naught equal 2. And I'm going to plug that in to find an x value that's closer to my true root than 2. So x1 is going to be equal to negative f at 2 over f prime at 2 minus 2. And when I put that into my calculator, I get 5 over 3. Now I know I'm going to use this again because this is just my first estimate, and I want to get a little bit closer to the true value. So I know I'm going to repeat this process again. So I'm going to save this into my calculator by storing it into the variable a. So I'm going to take this stored value, and I'm going to repeat this process to find a third x value. We'll call that x2. I'm going to take negative f at 5 over 3. I'm going to divide that by the derivative of f at 5 over 3, add that to 5 over 3, and I end up getting approximately 1.54861 repeated. So I know I'm on the right track because when I look here, I have 1 point something here and 1 point something here. So I know then that, or I can be pretty sure that my root is going to be 1 point something. But I want to get a little bit closer. So let's see if I can get this to be even more accurate. So I'm going to take this value, I'm going to store it into my calculator using the store feature. I'm going to put it into variable b, and then I'm going to use the variable b in my next formula that will allow me to calculate x3. So this is like my fourth point that I'm going to check. And I plug in my variable b, and this time my formula determines a value of 1.532390162. So you can see now we're getting a little bit closer. So here I had approximately 1.5, and here I have approximately 1.5 before the numbers are different. So I can tell now that my root is going to be pretty close to approximately 1.5. I'm not satisfied though. I want to get even more accurate. So I'm going to store this value into the variable c in my calculator. I'm going to repeat the process once again with my variable c, and this time I get 1.532088989, and I can see now that my two estimates, my x3 and my x4, are the same up to 3 decimal places. So I know now that my root is going to be approximately 1.532 something. So I could continue and I could take it further from here, but I think I'm satisfied with accurate up to 3 decimal places. So I can now conclude that f at x is going to have a root or an x-intercept somewhere around x equal approximately 1.532. Okay, so I've used Newton's method to help me, Newton's method and the idea of linear approximations, setting the y value equal to 0 and getting x values that are closer and closer and closer to that x, y value being equal to 0 to help me predict what the root is for this function that I might not have other strategies to use to be able to find the roots.